Hello, welcome back. The topic of this video is patient-specific QA. So that will be the QA tests that you do before a patient is treated to ensure that what you intended to deliver is actually delivered. Now I've brought in some help on this one too. Help me out, Joel. You can come up. How you doing, buddy?
Good.
All right. So what do you think about all this QA business? Good, bad?
Well, I don't even know what that means, so
You don't know?
I think it's good because you're talking about it too much. So yeah.
Okay, well, you're going to find out if you watch this video. All right. You want to show us your physics dance? I know you have a physics dance.
I'm trying to do the floss, but
You can't see
can't
it.
really see it, so I'll
How about
just
the other one? Oh, there you go. That's your physics dance. Very nice. I know you love physics.
I don't even know what physics is actually.
That's okay. You watch the videos, you'll know, man. All right. Okay, so we're going to start with this treatment plan. You've seen things like this before. And you want to verify that the actual plan as delivered on the patient is going to be delivered correctly. That's quality assurance. The problem here is the plan is pretty complex. As you can see here, you're rotating around the patient with this VMAT plan, and you can see the small segments as the arc goes around the patient. So you can't just visualize it on a patient like you did with a 3D conformal plan or so. So you have to have some alternative method. So the technique that's developed has been to verify it on a phantom device. So this is a measurement device shown here that's put into the beam, and you can measure the planned dose. So here's how it works in treatment planning. You've got a plan here on the patient, and then I copy it to a QA plan. I'm copying it onto the phantom of digital phantom that replicates the device you just saw. And here it is on the digital phantom. So a patient plan should look like this on the phantom, and you can measure it. So I export it. Then you line up this phantom device under the beam. Once it's lined up, you treat. You're seeing the arc around the phantom. So let me show you how this works. If I zoom in, you'll see it has an array of detectors. Each little dot here is a detector, which measures the radiation dose. So you can analyze this. I'm showing here the measured dose on the left and the dose from the treatment plan on the right. And you can draw a profile through these. The measured dose is the points here. So let me show you how this works. I'm going to draw a plot here and explain the analysis. So dose versus distance along the detector plane. And I'm going to draw an example plan profile here of dose. It has some sharp gradients because of the modulation. And here are the measured points from the detector. So how do you analyze this? So the problem here is that if you look at a particular point, it can actually be quite distant from the measured dose, even though you can see that it actually isn't deviating that much. It's just that it's in a high gradient region, but it's close to the planned dose in this region. So you need some way of accounting for this and analyzing it. So we use a special metric for that combines both the deviation in the dose and the deviation in the distance. So let me start by plotting some difference in dose here. Let me say 3% would be the allowed deviation. And then in the other dimension, I'm going to show the allowed deviation in distance, 3 millimeters here. And I can draw a circle that would account for both of these. So let me just shrink this down a bit so it's more realistic, and I can move this to the first measured point. Let's look at this point. Does this point pass? No, it does not, because it's not within that circle. Let's go to the next point. That passes. It's within the circle. Third point. That one's just at the edge, but it doesn't pass. It's not within the circle. So you go along marking each of these points. If it's within the circle of dose difference and distance to agreement, it passes. And you'll see here that most of these points are passing. So in all, we have 16 points and 14 of them pass. So that's a 87.5% pass rate for this particular field. So this is called gamma analysis, and the gamma is some combination of distance and dose, as I showed you. And this circle here is defined as gamma equals 1, and we can change the size of that circle. So going back here to the report analysis, you can understand this better now. So here I'm showing that 98.6% of these points pass, and that's with the 3% 3 millimeter criteria. And so that's, you specify that. That's, in other words, specifying the size of that circle in the gamma analysis. But I could actually change the size of the circle. So here it is with 2% and 2 millimeters. And you see that the pass rate goes down. Before it was 98.6, now it's 92.2, which sort of makes sense. The circle is smaller here. So now I'd like to talk about some of the devices that are used to make these measurements. I showed you this one, the cylinder. I'm going to mention some vendor devices here. I don't really have any particular favorites. This one is an array of ionization chambers. It's a flat array. Distance between chambers is 7.6 millimeters. Here's another one from a different company, and these are again ionization chambers, but the distance between them is 5 millimeters. So they come in a variety of forms, and here's a table just listed alphabetically showing some of the available options for the planar, the flat arrays. And then these planar arrays, you can put them either directly under the beam, maybe with some phantom material on top of it, or you could put them inside a specially designed phantom, like that might be, say, a cylinder or something, and then if you correct for the angular response of the detector, you could do an arc around the detector and get a good reading. So I don't know, hopefully I've listed most of the major ones here. I don't know if I've gotten every single one, but if you see one that you like that's not here, let me know. And then here are these non-planar devices. We already looked at the first one. The second one has an interesting design. It has a biplanar array of diodes to measure in 3 dimensions. So here's what the device looks like, and here you can see the 2 planes of detectors that extend into the cylindrical part. And then here's just sort of a newer version of that that's wireless. So one of the key things about these devices is the resolution, so the spacing between detectors, let's say. So if I go back to this image, you see if I measure each of these red points, the more points I have, the better I'm going to be assessing this dose distribution. And that can be important when you have either very sharp gradients and or very small fields. So in that setting, you've basically got 2 options. So one is you go back and use film, okay, because that has a very high resolution. You can insert film in a phantom, and you can measure it and do the dosimetry and compare it to the treatment plan, and we sort of went through a bit of that in the previous lectures. There are disadvantages to that. It's not immediate. There's calibrations that are needed that are complex, and so on. Another option is that you can buy specialized array devices that have slightly higher resolution. And here are a couple of those. And those will give you immediate readouts. And again, those would go in some sort of phantom. Now let me describe a third type of option for these QA approach, and that is to use the EPID on the linear accelerator itself. This image shows the arrangement. So here's the EPID. That's the electronic portal imaging device. We're going to talk a bit more about EPIDs and how they work in the video about imaging. But for now, it's a device on the Linux that allows you to image the megavoltage beam. So then you take that image and you turn it into a dose, and then you can compare that dose to the dose from the treatment planning system, and that's your QA. So here I'm showing it with a phantom in the beam. You don't have to have a phantom, you could do it in air, but the procedure is the same. There are some challenges to this because you have to, in turning that image into a dose, it's complex. You have to correct for scatter, you have to correct for energy response in the detector and other effects. So it's a bit of a work in progress still, but this is one direction things are going, and the advantage is that you have a very high resolution image. The EPID is sort of similar to film in its resolution. So now I'd like to talk about 2 other approaches to QA that you need to know about. So one is Invivo QA. So that means taking a measurement during treatment with the patient on treatment. And then the second is an approach where you don't take measurements on either a device or on the patient, but you rely on other methods instead to assure that you have good QA. So both of these approaches, they might be used in combination with the other approaches that we already talked about, doing a measurement before treatment. And I think it's somewhat more controversial to use them instead of that approach, but some people are also doing that. So let's talk about Invivo QA first. You've already seen these. These are diodes for in vivo dosimetry. You can go back and look at video 17.1 to see this. The problem is these are just single point measurements, so they're not great for looking at spatial variations in an IMRT field. We talked about this. This is an EPID QA. You could do this with the patient in the beam, and that would be called in vivo EPID dosimetry. In that case, you're measuring the exit dose from the patient, and you can backtrack and figure out if it's what it should be coming through the patient. An alternative approach is to look at putting something up here in the head of the linear accelerator and try to do some measurements during treatment. So let's look at one of these systems. Here's a device that clamps on to the head of the linac, and it measures the dose coming through it as you treat. So that's before it reaches the patient, confirming that the beam is right. You can see here that device slides out of the way so you can see the light field. There are a few such devices like this on the market, and here's a list of what's out there currently, and it's probably growing as we speak. One of the things that you worry about when you put anything in the beam before the patient is how does it affect the skin dose, the superficial skin sparing that should happen. But that's been measured with these devices, and it's thought to be relatively small. So now I'd like to say a few words about these non-measurement based QA methods. And actually there's a lot of words I could say, but I'm going to try to keep it brief. So you've seen this delivery movie before. You can go back and look at video 14.1 and look at this. But as these fields are delivered, a log file is written to the computer that describes every MLC position, every MU delivered, and you can use it. So here you have a fluence map from the treatment planning system, and then you can calculate the fluence map given what's in the log file, and you can compare those two. So that's a sort of an indirect calculation-based method for IMRT QA. Now that we've talked about patient-specific QA, I'd like to talk about some of the references and standards that go behind this. The most recent report is Task Group 218 from AAPM. That was published in 2018. It talks about the methods for IMRT, QA, and the tolerance limits for tests. And by the way, the links here in the video should be clickable if you're viewing with the right player. We have AAPM Task Group 119, published in 2009. That talks about commissioning IMRT and some of the tests that are associated with that. And then that group actually has a downloadable test suite. So these are CT scans and volumes that you can do your own treatment plan. You can download those and you can compare it to the results. And then finally, there's an older report, AAPM Report 120, talks about dosimetry tools and techniques, and there are some other older reports in this vein. So these are what I would call how-to reports, sort of how to do things, the techniques and tools. There's also some other reports from other professional societies. And here's one, the Astro Safety White Paper on IMRT, published in 2011. That's part of a general series of guidelines and consensus statements from Astro, and here's a link to the website. Up to now in these videos, I've talked about physical aspects of QA, so doing measurements or computer checks, but there are other aspects of patient-specific QA that I want to talk about that are in the realm of reviewing plans and charts before they go to treatment or during treatment. And I'd like to motivate that a little bit. So here's some data. This is showing a series of different checks that are done in practice and the effectiveness of each of those checks for catching errors. This is work from our group. This is when I was at Johns Hopkins, and we combined our error database with that at WashU, and collaborations with Sasha Mudich and others there. So you may have seen this figure before. It seems to appear quite frequently, but let me walk you through it. So up here at the top, you have plan or chart review by a physicist, either before treatment or on a weekly basis, and then the same thing by the therapist. Those are very effective measures at catching errors according to this database. A little further down, physician chart review, and then further down here, chart rounds, or you'll often hear it called, physicians call QA chart rounds. That's peer review of the disease management by physician peers. So there's a lot that can be said about these various checks, and it's difficult to be too detailed in a short video like this, but let me point to some recommendations and new knowledge that's emerging about these checks. So let me start with the top, talking about plan review by the physicist. That's the topic of an upcoming report from the AAPM, Task Group 275, that will be published in 2019. And that describes strategies for plan and chart review by the physicist. What should be checked, the frequency, and a sort of a risk profile associated with that. Going back down here to the QA chart rounds, that's another area where there are now some recommendations by professional societies. One thing to note is that the effectiveness does not really look that great here. The effectiveness is low, but what this graph doesn't show is what happens when you combine these checks with each other. It's discussed in the paper, but basically the idea is that each check can potentially probe a different dimension of error, and so they're potentially much more effective when they're used in combination with each other. And chart rounds in particular probes a dimension that other checks can't get at, because the knowledge and information and judgment of a physician is not something that's really accessible to other professional groups that are involved in the process of care. So peer review. So one key reference is this Astro Safety White Paper on peer review, published in 2013. This is led by Dr. Larry Marks and physician and physics colleagues from Astro. And I won't go through all the details in this paper and these recommendations, but here are some key things here. So they talk about the need to review target definition. They talk about the need to look at the decision to include radiotherapy and the directive around that, the general radiotherapy approach, and the effects on normal tissue. And then they also talk about review of plan quality and say that that's something that dosimetrists and physicists can and should review. All right, so there you go. Those are some of the basics of patient-specific QA. It's a very vast and complex area of medical physics. I'm going to leave you here with a few further readings and references, but the reality is there's actually a lot published on this topic and a lot that could be said about it. But I'm going to just leave it here, and we'll see you in the next video.